So till now we have seen about the 8085 architecture, features, addressing modes and instruction sets. So in this video lecture we are going to see about the timing diagram of 8085 microprocessor. So timing diagram which is nothing but the timing diagram which is nothing but the graphical representation of the execution of an instruction. So we know that if you want to write a program, we are in need of n number of instructions to develop a program. So each and every instruction has to be executed and it has to pass through three stages that we have discussed in the architecture itself. So like fetch, decode, execute. Okay, fine. So the execution of an instruction is more important. So we are going to graphically represent that execution of an instruction. So we will see that now. So as I told you, timing diagram is nothing but the graphical representation which represents the execution of an instruction, right? Okay. So for example, I will show you a timing diagram of an instruction. So this is the timing diagram of the instruction STA526A. So this is how the timing diagram will look like. So we will have a clock signal, address lines, data lines, ALE, read, write, all those things. So we will represent the execution of an instruction like this. Okay, fine. The clock is most important for this. With respect to the clock, we will represent all those signals in the timing diagram. So this is how the instruction STA works. So before we see the timing diagram, we should know the important topics or concepts of timing diagram. We will see it one by one. So first thing is instruction cycle, and second thing is machine cycle, and third thing is T state. So the first one is instruction cycle, which is nothing but the time that the instruction takes for an execution. Okay, so the total amount of time that an instruction required for an execution is known as instruction cycle. So which is nothing but time required for the instruction execution. So complete execution, the time required for complete execution is instruction cycle. Then machine cycle. So machine cycle is nothing but the time required for the instruction to access the memory or input output device. Fine. So it's different from instruction cycle. Instruction cycle is the total amount of time that an instruction requires for its execution, but machine cycle is the time required for the instruction to access memory or input output device. So it is just a part of instruction cycle. Fine. So which is nothing but time required to access memory or input output device. Fine. Okay. The next thing is T state. So we will represent the T state as a clock cycles. So it will be like the pulse signal. It will be like this. Fine. Okay. So T state is nothing but a portion of an work done during one system clock, that is T state. So one system clock is nothing but one low pulse and one high pulse. So this is called as one system clock. Okay, the operation done during this one system clock, the operation done during this one system clock is known as T state. Okay, fine. So I will explain you with the sample timing diagram. So in this instruction, the machine cycle, the total time required for this execution is this thing. This is known as instruction cycle. So and a part of it. So this instruction STA has to access the memory in order to store the value in the accumulator, right? So the time it takes to access the memory. So this cycles. So memory reads. Fine. So these are all called as this opcode fetch also. Okay, these are all called as machine cycles. Fine. So can you get me? I will tell you it once again. So this store instruction, how it will work? STA 526A, which means that the value in accumulator will be stored in the memory location 526A. That is the operation here. So which means that this instruction is going to access this memory 526A. So obviously it could be a machine cycle because it's accessing the memory. Fine. So in case of in and out instruction, we will access in and out instruction. Fine. We have seen no in out. Okay. In case of that, we will access the input and output devices. So here we are performing memory write operation. Why? So the value here, for example, 5, it will be written here. So it's a memory write operation. Fine. So these things are called as machine cycles. We will discuss each and every machine cycle in detail. So now you just know it. And next thing what we have said about that is T state. So T state is nothing but the operation done in portion of an operation done in one system clock. One system clock is nothing but one low pulse, one high pulse. This is one T state. So another low pulse, another high pulse. This is another T state. Okay. The operation done during this T state is this one system clock is known as T state. This is T state, and this is machine cycle. Fine. So can you be able to identify the difference between these things? Okay, fine. So now we will see about the machine cycles. So as I told you before, the machine cycle is nothing but the time required to access the memory or input output devices. Okay, fine, as we have seen here. Okay. So the operations that we do during the operations that we do for accessing the memory or input output devices could be like opcode fetch, then we will do memory read operation, then memory write. Okay. So in input output devices we will do IO read, then IO write. So then interrupt acknowledgement. Fine. So these are all the 6 machine cycles so that we use in the timing diagram. Fine. So once again we will see what are all the machine cycles: opcode fetch, memory read, memory write, input output read, input output write, and at last interrupt acknowledgement. So all these machine cycles will have some T states. To perform its operations, it will occupy some T states because T state is the basic unit in the timing diagram. Fine. So to perform an operation, T state is most important. Okay. So we will see how many T states each and every machine cycle occupies. Fine. So the first one is opcode. So it will occupy 4 T state or 6 T state. So 4 T state in the sense 4 low and high pulse. So this is 1, fine, and this is 2, and this is 3, and this could be 4. Sorry. So 4 such T states it's required to perform an opcode fetch operation. So memory read, it will take 3, memory write, it will also take 3. Both input output read, input output write separately will have 3 T states. So interrupt acknowledgement, it will take 6 T state or 12 T states. Fine. So we will see each and every machine cycle in depth, how it takes 4 or 3 T states. Fine. So first we will see about opcode fetch machine cycle. So what is opcode fetch? So each and every instruction, this we have seen before itself during while we are discussing about architecture. So each and every instruction will have a separate hex code called opcodes, which is understandable by the processor. Fine. Okay. So for example, if we take the instruction LDA 4500, so what's its operation? So it will load the value in 4500 into the accumulator. That is its operation. Fine. The opcode of this LDA is 3A, which you all know. Fine. So this you have seen in the lab classes itself. Okay. The opcode for LDA is 4A. Okay. So what during this opcode fetch, what will happen? The processor will look into this opcode and put it in the instruction register. Fine. This we have discussed in the architecture itself. Okay. So this instruction we will store in a memory. Assume that the address of this memory is 6500. So how this would be stored in the memory? At 6500, first opcode will be stored. Fine. This is the opcode. 3A is its opcode. So and then at 6501, what will be stored? This address will be stored. Okay, the first lower byte will be stored, and next the higher byte value 45 will be stored. Fine. So in order to know this, in order to fetch this is the opcode, right? In order to fetch this, you have to perform opcode fetch operation. For this single instruction, first you have to perform opcode fetch operation. So during opcode fetch, what will happen? The processor will look into this address, get this value, and it will put it in instruction register. So later from the instruction register, it will be transferred to instruction decoder, where the operation corresponds to 3A will be decided. Fine. This we have discussed in architecture itself. Fine. So the operation of opcode fetch is, it will get the opcode value from the memory and it will place it in the instruction register. So that is opcode fetch. So now we will see. So it occupies 4 T states. So this we have seen here. Fine. So how it occupies 4 T states, that we will see now. So this is the timing diagram of opcode fetch, which has 4 T states: T1, T2, T3, T4. Fine. Okay. So before I tell you this, I have to tell you one thing, which is so before I tell you the opcode fetch, I have to tell one important thing, that is how the processor makes a difference, or how it knows whether you are performing opcode fetch, memory read, memory write, input output read, and input output write and all. Fine. So how it finds? So it finds using the control signals. So control signals are IO/M bar and the status signals S1 and S0. So with the values of these 3 signals, your processor will find out what machine cycle it is performing. Fine. That we will see it now. Okay. So as I told you, the control signals are IO/M bar, S1, S0. As a whole, it is called as control signals. So these 2 signals are called as status signals. Fine. So if the value of IO is 1, which means that you are performing IO read, because it's 1, but the complement of 1 is 0, so this will not be performed. Okay. So if this value is 0, means this will be 0, IO operation will not be performed. Complement of 0 is 1, so the memory operation will be performed. Okay. So if the value is 0 and the status value is 1, 1, then the operation is called opcode fetch, because the opcode is stored in the memory itself, so it's a memory operation. So we have written here as 0 and status signal values are 1, 1, 1. So if the signal value is 0, 1, 1, then the operation is called opcode fetch. Okay. If the signal is 0 and this value S1 is 1, S0 is 0, then the operation is memory read. Fine. So if this value is 0 and if it is 0 and S0 is 1, then the operation is memory write. Fine. So if it is IO read, what would be the value? S1 value will be same as here 1 0, but here it varies because you are accessing IO and not memory. So the value could be 1. So if it is IO right, then the value would be 0 1 and here it is 1. Okay, fine. So the control signals plays a major role in the timing diagram. It is most important. So you could or you should know about these things. Fine. So now we will see about the opcode fetch. Okay. Okay, I've told you that opcode fetch takes 4 T states. Okay. Here you see, so this is an opcode fetch cycle which takes 4 T states. So first load to high, second load to high, this is second T state, third load to high, third T state, and 4 load to high, 4 T states. Fine. So this is a clock signal. This is most important thing. Fine. So at the first T state, what will happen? That we will see now. So for example, we have taken this instruction previously, LDA 4500. Okay, this instruction is stored in 6500. In memory, it will be stored like 6500. 3A will be stored, which is nothing but the opcode. So at 6501, this address lower byte will be stored, and 6502, the higher byte address will be stored. Fine. So during opcode fetch, this operation will happen. It will look into this address. Fine. So to get this opcode, you should know this address, right? 6500. Where you will get this address? So this is the instruction address, right? Where you will get it? You will get from the program counter. Okay, program counter will have this address. So at the first T state, fine, you have to get this address. Okay, and you have to get and you have to place it in A0 to A15. Okay, so in the 8085 processor, we know that lower byte data and address are multiplexed and higher byte will remain the same. Fine. So in this lower byte, your lower byte address, which is 00 will be placed. The higher byte, the address 65 will be placed. Fine. So once the processor sees this address, it will go to this address, see to the opcode, take it and place it in the instruction register. This is what happens when you perform opcode fetch. Fine. We will see this in the timing diagram. Fine. So at the first T state, what you have to do? We have to fetch this 6500. So at first T state, what will happen? The first important thing is IO/M bar and control signals will have the value 0, 1, 1. Okay. So before I tell you how the signals are represented, so when you are representing a single signal, we will use this like this, a single line. Using single line, we will represent a single signal. Okay. So when you see here AD0 to AD7, which is nothing but 8 values, no? So you are representing it as bus. So you have to represent like this. Fine. So when you see here, we are representing 3 signals, IO/M bar, S1, S2. So you are representing it as bus. Inside the bus, you are mentioning the value. Fine. So the read bar, it's a single signal, so it is represented like a single line. Fine. So this cross represents the change in the value. So before this, some value it might have. So after this cross, which means that the value of this bus has been changed. Fine. Okay. So now we will see about this thing. Okay. So in the first T state, so your IO/M bar S0 S1 value should have this value. Okay. I will write here at T state 1. What will happen? First thing, IO/M bar S1, S0 will have the value 0, 1, 1. This has to be changed in the first T state, and it should be retained throughout this opcode fetch operation, which means that throughout this T4. Then only the processor knows that you are performing opcode fetch. Fine. So the next thing what should happen is it has to fetch the value from address from where it has to fetch PC from program counter and place it in AD0 to AD7 and A8 to A15. So in this example, what value will be placed in AD0 to AD7? Which is nothing but 0, 0, lower byte, no? So 0, 0. So and higher byte value is 6, 5. Okay. So this value would be put in this thing. So I will write in different color. So from AD0 to AD7, what value, lower byte, no? What value will be there? 0, 0. So 0, 0 will be placed here. So in A8 to A15, what value? 65. 65 will be placed here. So this will happen in T state 1. Okay. So the next thing, so we have put the address values, and next thing what you have to do, you have to make this address latch enable high. So why you have to use this signal? Because the lower byte AD0 to AD7 is multiplexed. Okay. So multiplexed in the sense in the same line both data and address will access. So in order to what do you mean by multiplexed? Which is nothing but your address and data are your address and data will travel in the same lines. Okay. So what you have to do, which means that the processor has to make or know the difference between the value of the address and the value of the data. So for that you are using the address latch enable. If that address latch enable is high, okay, what does it mean? The processor, by seeing the address latch enable, if it is high, it knows that the value in that bus, multiplexed bus, will be address. So if that address latch enable signal is 0, which means that the value in the address data multiplex bus will be the data. Fine. So here we are making it high. By seeing it, the processor knows that the value in this bus is 0, 0. So now see in this timing diagram, you are making the address latch enable high. Okay, that is made high only in this T state 1 and not in other T states. So which means that the value that we put in the AD0 to AD7 0, 0 is nothing but address and not the data. So which is which we have seen from this thing. Okay. So this will happen in T state 1. So the next T state 2, what will happen? Now the processor knows the address, which is nothing but 6500, because that was put in the address bus. So now the processor knows the address value of the instruction, this instruction, which is nothing but the opcode, knows the address of the opcode. Now the processor has to go to this location and it has to take this opcode, which is nothing but 3A. Fine. It will be like stack, no, memory 6500, which has 3A. So now the processor knows this address 6500. Now the processor has to move on to this 6500 and it has to take the opcode and it has to place it in instruction register. At T state 2, the processor will knows this address, go to this address, okay, take that opcode value and place it in, it takes the opcode value, place it in AD0 to AD7. Okay. So why it's placed in AD0 to AD7? Because it's considered this 3A as a data. Okay. So it will consider this 3A as a data. So it takes and put it in the AD0 to AD7. Okay. So now we will see this timing diagram. At T2 state, we will have one high to low signal. Okay. There is no change in the higher order address, so it will retain as such. 65 will be retained here also. There is no change in this IO/M bar and the status signal. Okay, fine. The change has to happen in address latch enable because you are fetching this 3A and you are placing it in the same lines, lower byte address and data lines, which is nothing but a data and not the address. So it is made low. Fine. Okay, so in order to read the value from the memory, you have to perform read operation, correct? Okay, we are not writing into this location, we are getting the value from the location. So this operation is called read operation. So obviously we have to use the read signal. Okay, so it has mentioned as RD bar, which is nothing but active low signal. Active low in the sense, if you give 0 only, this signal will be enabled. So why it is? So 0 bar, you are taking complement of this 0, so it will become 1. So if you are giving 1 means 1's complement is 0, so this signal will not be enabled. So that's why at t state 1 this signal is high, which does not have any impact here. So what happened in t state 2? You are reading the opcode value from the memory. So the signal has to be low in the t state 2. Okay. So first thing, your read signal should be low to read the opcode. Fine. So this will happen in second t state. Now we'll see third t state. Okay. So what will happen in the third t state? So in t state 3, it will place the opcode value to the instruction register. Okay, this will happen in t state 3. Okay, so when you see this timing diagram at t state 3, so the higher order address will remain the same. Opcode value we will have, it will be in the address bus. The status signal does not vary. ALE should be low, and this signal should made in between as a high. Okay, at this place, this opcode will be placed in the instruction register. This will happen in t state 3. Okay, so next we will see t state 4. At t state 4, what will happen is the opcode that we have fetched from the memory, okay, that will be decoded. So what do you mean by decoding? So the opcodes are nothing but the hex value. The processor during the decode operation will knows what corresponding operation that it has to perform by seeing this opcode. Okay, so as I have already told you, for each and every instruction we have an opcode, which is nothing but the hex code. Fine. So by seeing the hex code, the processor has to come to a decision what operation it has to perform. Fine. So that decision is taken during the decode operation at the T4 state. So at T4 states, it knows what operation it has to perform. Okay, so that's all about opcode fetch. Can you all get it? So once again we will recollect it. So opcode fetch is nothing but it will fetch the opcode in the memory and place it in the instruction register. This operation will happen during the opcode fetch machine cycle, okay, which takes 4 t states. So at each and every t state, some operation will happen. So at t state 1, what will happen? So your control and the status signal should have the value of 0, 1, 1. So you see here, your control signal should have the value of 0, 1, 1 to represent that this operation is an opcode fetch. So on the second thing, it has to get the address of the opcode from the program counter and place it in the lower and the higher address lines. So and your address latch enable should be high at the t state 1 in order to make the difference in the lower byte address and the data lines. So at T2 state here, okay, at T2 state, what it will happen? It will move to this address location, get this opcode value and place it in the data bus. Okay, so for that your read signal should be low. So when it is low, it will read the value from the memory and place it in the address bus. Okay, so there won't be any change in the higher order address. We are not going to disturb it. Fine. So at T state 3, what will happen? The value that is placed in the data bus will be placed in the instruction register. So at T4 state, that value in the instruction register will be decoded, which means that the corresponding operation of the opcode will be decided. Fine. So this is what opcode fetch. So next we will see the second machine cycle, which is nothing but memory read machine cycle. Okay. So as we have seen before, the memory read machine cycle takes three T states. Fine, that we have discussed before itself. So and how the control signals would be, because the processor has to know the operation that we are performing is memory read, no? So how the value should be? Yeah, yes, the value is 0, 1, 0. Fine, we will see the timing diagram now. So this is the timing diagram for memory read cycle. As I told you, it has three T states which has 0 to high, okay, signals. Okay, so your need of clock, that is most important, as your address and data lines, address latch enable and control signals, then read bar, because we are performing memory read, so read signal should be there. Okay, so we will see what happened at each and every T state. So at T state 1, what will happen? As a first thing, the control signal values, you have to change it. So how the value should be? So this, you are performing memory operation, so 0. So read operation is like S1 is 1, S0 is 0 to represent the memory read operation. So and second thing, what you have to do? Yeah, you have to know the values address. Now for example, if you want to take the value 32 from this memory location, for example I am saying, so if you want to take the value 32 from this location, you should know this address, right? Okay, so at the second thing in the T state 1, the value, this address value will be put into the address and the data bus. So A8 to A15 will have the higher byte address 45, and AD0 to AD7 will have the value 00. Fine, for example I have taken this. Okay, so as a third thing, what will happen? So in order to differentiate this, whether this value is address or data, you have to make this high, because this 00 is an address value, lower byte address value, so this address latch enable should be high. Okay, we will see this in the timing diagram. At T state 1, okay, you have to take the value, higher byte value, that is 45 will be placed here, then 00 will be placed in the lower address, and the address latch enable should be high, and the control signals value should be 1, 0, 0. Okay, this value should be retained. The signals that does not change throughout the cycles are, one thing is higher order address lines, and another one is control signals. So other lines will vary, depend on the operation. Fine, so and the read bar should be high, because we are not reading anything. Okay, so the read signal should be high at T state 1. Okay, so next we will see what happened at T state 2. So this is the memory read operation, right? Now we know the address 4500. The processor, what it has to do, next it has to look on to 4500, take this value 32, which means that it has to read this value 32. So for that, in order to read this value, your read bar should be low here at T state 2. So now we look on to the timing diagram. There is no change in the address, no change in the control signal. Your address latch enable should go low, because you are taking the value, this is the data, right? You are taking the value and you have to put it in the data lines. Okay, so in order to represent this as a data, your address latch enable should be low. Okay, so you are performing read operation, so read bar should be low, so that the processor goes to this location, read the value and put it in the data line. So now this bus has the value 32. Fine, so at T state 3, what will happen? We will see now. At T state 3, so as of now we know the address value, and from the address it has fetched we have read the value 32. At T state 3, as per the instruction, this 32 will be placed or copied in the register mentioned in the instruction. Okay, fine. So if you have mentioned B register, then this 32 value will be written in B register. It depends on the instruction. Fine. So at T state 3, that will happen. The value in the data bus will be written or copied to the register mentioned in the instruction. Fine. So you all familiarized with memory read cycle, no? So once again we will recollect it. So memory read is nothing but it will take the processor. It is nothing but the processor will take the value from the memory and place it in the register that we mentioned in the instruction. Okay. So as I told you, it takes 3 T states. In the first T state, what will happen? The control signal values 0, 1, 0 will be there, and the value of the address of the value will be taken and placed in the address lines, and address latch enable is high at T state 1. So that you can see here. At T state 2, your read signal should be low, so that it will read the value from the memory location 4500 and place it in the data bus. That is nothing but 32. Fine. And at that time your address latch enable should be low. Fine. So at T state 3, this 32 value will be written into the register, or placed into the register mentioned in the instruction. Fine. So this is memory read cycle. So next we are going to see about memory write cycle. Okay, this is quite different from the memory read cycle. So in memory read, we are going to read a value from the memory location. In memory write, you are going to give a value to a particular memory location. Okay, which is nothing but a write operation. You are going to write on a particular memory location. So as we have seen before, this memory write cycle occupies 3 T states. Fine. So we will see that now. So this is the timing diagram for memory write cycle, which occupies 3 T states. So the signals are same. So only the signal that varies is write signal. Fine. So at T state 1, what will happen? The IO / M bar S1 S0 value should be 0 because you are performing memory write. S1 is 0 and S0 is 1. So then you have to place the, for example, you are writing, you are going to give a value to the memory location 6505. Okay. Okay, consider this, you have to write a value in this location 4505, a value of 68, for example, I am saying. Okay. So now at the second cycle, you should know this memory location 6505. So this will be known and put into the address lines A8 to A15, where the higher byte will be placed 65, and AD0 to AD7, where that value will be placed 05, and as third thing, your address latch enable should be high here. Fine. So this is what happened in T state 1. Okay. So as usual, clock signal, here the value 65 will be placed and lower 05 will be placed. Now this is the address. So the address latch enable is high. So we have discussed 001. So at T state 2, what will happen? So for example, you have having this value from the B register, 6A is placed in the B register. So at T state 2, what will happen is the processor takes this value from B register 6A. So that will be 6A or data, I am writing the general thing. Data will be placed in data bus, which is nothing but AD0 to AD7. The value from the register, here I have used B register, the value from the B register is taken and placed in the data bus. So at this point, at T state 2, this will have the value 6A. Okay. So at T state 3, what will happen is the value in the data bus, okay, the value, that means your data in the data bus will written in the memory location that was fetched in the cycle T state 1. So that is nothing but 6505. Fine. The value in the data bus, that is nothing but 6A. that we have taken as an example, no, the value here will be written into the location 6505. That will happen at t state 3. Okay, so this will happen. See this timing diagram. At this point it will be write. We are performing a write operation, so the write bar should be high because it's an active low pin as of read signal. Okay, fine. So once again we will recollect this memory write cycle. Starts T3 T states. At T state 1 the control signals value should be 001, and it will fetch the address values where we want to write the value. For example, we have taken this address, so higher address, lower address will be written in the bus, and address latch enable is high. At T state 2 the processor will take the value to be written from the register and place it in the data bus. Okay, at T state 3, at that time address latch enable should be 0. Okay, so at T state 3 the value in the address bus will be written into the location that we have known here. Okay, that we have already fetched. Okay, at that time during write operation write bar should be low. Okay, so this is how opcode fetch, memory read and memory write cycle will happen. So next we will discuss about IO read and IO write. So the memory read, memory write and IO read, IO write are similar. The operation, the T states are the T states that it occupies also same. Memory read, memory write, IO read, IO write. So all these 4 things occupies the same T states, 3 T states. Okay, that we have discussed before. Fine. The operation is also same, but the slight difference is in memory read it's accessing the memory, in IO read it's accessing the IO devices. That is the only difference. So the difference that we have to make is only in the control signals. Fine. So the difference that I have to make is here. So status signal there is no difference. If the value is 1 0 it is read, if the value is 0 1 it is write. Okay, so this signal is only decides whether we are performing memory operation or IO operation. If it is memory you have to write 0, if it is IO you have to write 1, that's all. So there is no change in the diagrams also. See here, so this is a memory read cycle and this is IO read cycle. T states are same. Fine. So here in this address, first we will see about this IO/M bar, this value should be 1. Here you see this value is 0 because you are performing memory operation. Here you are performing IO operation. Fine. So this there is a change here. Fine. So in the memory read at T state 1 here we are knowing the memory address value, right? Okay. So but here we are knowing the port values because the input and output devices are represented by the port address. We know that, right? We have discussed it before itself. Each and every port address is of 8-bit. Fine. So that 8-bit address is placed in the both higher and the lower address. So but it will consider here only, it won't look into there. Fine. So at that time address latch enable should be high. So once in read operation we are performing read only, no. At T state 2 the processor will look into the address that in port address. So for example, if I have 38 as a port address, it will look into this port address which is nothing but where our device has been connected, take the value, which means reads the value at T state 2, so the read bar is low. Okay, and place it in the accumulator because at T state 3 the value that it has read, for example 42, which will be placed in accumulator at T state 3 because while we are discussing the instruction set we have seen that in and out operation has to be happen through accumulator, that we have seen during the instruction set. So at T state 3 the value 42 which is read from the port address 38 will be written into the accumulator. This will happen in T state 3. Fine. Okay. So next we will see about in and out in IO write cycle. So IO write cycle, this is similar to memory write cycle. Okay, the difference is here that we have seen in the previous thing also. Fine. First at T state 1 we will know the port address. Okay, so at T state 2 it knows the value from the accumulator. From accumulator it takes the value and put it in the data bus at t state 3. The value in the data bus will be written into the port address that we know here. For example, if we have 92 as a port address, at 92 the value in the data bus will be written, which means that this value 92 is given to the output device. Fine. Okay, so now we all know how the timing diagram is. So what you have seen is just the timing diagram of the machine cycles. We didn't look into the instruction timing diagram. That we will see in the next video lecture.